something just wonky just happened. So I'm just going to go as if things are working. Ah, good. All right, very good. Hello, everybody. Welcome to this month's Astro Coffee Hangout. My name is Tony Darnell. I'm from deepastronomy.space, and today we're going to be talking about with members of the Dark Energy Survey collaboration, which is an interesting group of people who are trying to understand why it is that the universe is accelerating as it expands. Now, anybody who's watched the videos on our channel for any length of time has heard about dark energy, has heard about the fact that the universe is expanding, and that it is accelerating as it does so, but we don't exactly know why yet, and many astronomers are trying to figure that out, but they are saying that whatever it is that is causing this expansion or the acceleration of the expansion of the universe is coming from either something that's a force that they're calling dark energy, for lack of a better word, or it might be something about gravity that we don't understand at very large scales. But right now, most people, I think, are leaning towards this dark energy idea. And so to try and figure out what it is, several astronomers from all over the world and in a variety of different ways are trying to figure out what this stuff is. And the members of my team, or my guests today, are members of a team who are operating a telescope, the 4-meter Blanco telescope down at Cerro Tololo Observatory in Chile. And they are looking for this stuff by building a massive camera, and I'm going to have our guest talk about what that camera is like in just a minute. It studies a huge area of the sky, 5,000 square degrees of sky in the southern hemisphere, and it's going to be doing it over roughly 525 nights to try and figure out what this stuff is. So we're going to get an introduction into that camera and that survey, as well as some of the science they're doing. But it turns out that when you have a wide field camera, and when you have a lot of data taking over a very long time, there's a lot of other really cool science you can do with it besides just look for this dark energy stuff. And today we're going to be talking about 2 separate papers that have been published using the data from the DECam, which is a dark energy camera that they've mounted on this telescope. And they've done some really amazing work with finding out they did some follow-up observations on the gravitational wave event that we've heard about last year, as well as looking at dwarf galaxies. And so we're going to be talking about all of that today. But before I get too far along in it, I want to introduce my co-host, Dr. Carol Christian. Let me pull her up. Hi, Carol.
Hello. How are you?
How
is everyone?
It's so good to see you again. You know, I haven't seen you since most of the summer. I guess we've both just been so busy. It's good to know.
I know, and I passed right by you because I did go to Florida.
Are you in Florida? Oh, you already went and came back?
I was in Florida, drove right by. Sorry.
That's all right.
Next time, I promised I'll
just wave as you go by. But anyway, well, it's good to see you again, Carol. I'm glad that we're able to connect again, at least during these Hangouts. But this is the time where you introduce these Hangouts, what we're doing and who made them possible and all that other kind of stuff.
So in many research institutions and universities, scientists and astronomers in particular get together for what's called science coffee. And depends, some departments have science coffee every day, some of them once a week. And the idea is to talk about lots of things, but primarily science papers of interest to the group. And the nice thing about it is that we exchange ideas about science papers that we may not be reading for our own science, but it makes us aware of the other kind of science that's going on. And sometimes during science coffee, we're really fortunate to have a visitor who comes and talks to us about their research very informally. And those are kind of some of the best exchanges. So when we were tossing around this idea, we thought, why should we restrict it to our own library or our coffee room? Why don't we open this up and have dialogues with the researchers who are doing the research and find out what they did, what they were thinking about, what kind of data it took, what kind of models they made, whether the models worked out, and what they're going to do for their research in the future. And so the idea of Afternoon Astronomy Coffee is to invite you in to coffee. And happily, we're supported by the American Astronomical Society and the American Astronautical Society, which is kind of the astronomy science and the engineering side of astronomy, both in space and on the ground. So we're very fortunate today to have a really interesting topic, dark energy, and a really interesting telescope built for that purpose. But as Tony says, when you do surveys, it's always interesting to see what else you can learn with the data. And that's why surveys and archive data are very powerful, because all kinds of interesting science can be done with that kind of data.
Yeah, and I would just mention real quick that I had the privilege of working with in the Dark Energy Survey group for about 2.5 years, many years ago, before the camera was way finished, and it was really a great group of people. Lots of people get involved in astronomy these days, folks, and these collaborations become huge. LIGO was one collaboration, the gravity wave people, and now, of course, we've got the Dark Energy Survey. And so, without any, and I should also, before I introduce my guest, just say, I'm streaming on about everything that can be streamed on right now, Facebook, YouTube, Twitter, and Twitch. And I'm looking at the live chat on YouTube right now, and my colleague Carl Clark is standing by. He is also driving the internet and looking at all of these other social media platforms. He's also live tweeting on Twitter at Deep Astronomy, and also as himself as Carl Clark. So welcome, Clark, and thank you. And by the way, Carl, if you see some comments or questions that are relevant to what we're talking about, please just blurt them out, and we'll
fire away. And everybody listening, just ask, because y'all ask great stuff.
Yeah, good. So, okay, great. So, all right, let's go ahead and let me get to my guests. Let me pull them up here and make them big and get rid of that. Okay, so today we have with us, as I said, people from the Dark Energy Survey collaboration on the... this may be mirrored, so I'm hoping I'm getting this right, but the one guy is the one male in the picture is Dr. James Annis. He is an astronomer at Fermilab, and in the center there is Dr. Marceli Soares Santos. She's a physicist at Fermilab, and she's also part of the gravitational wave follow-up program that we're going to be talking about. Also next to me is Dr. Ting Lees, a postdoc at Fermilab, and she's working on Milky Way science and looking at small and different kinds of galaxies. So welcome, guys. What is the deal with Fermilab? First of all, I thought, last I checked, Fermilab was a particle accelerator and particle. Now, Marceli, I get you. Why, you're a particle physicist, right? Why are you in this? What is it with Fermilab and dark energy? I don't get it. Why aren't we at an observatory somewhere?
We turned into the dark side.
You're on the dark. No, but it's true.
Yeah.
But that's true, though, isn't it? I mean, there's particle physicists are now becoming interested in cosmology, aren't they?
It's true.
Yeah. You look ashamed. Don't look ashamed. It's okay. You look like you've been condemned.
We dragged her in there. You have to go work with those astronomers. Oh no! Please.
No Higgs bosons for you.
I think I'm not the best person to tell this story. I think Jim was actually around at the time that the lab started to get more involved in astronomy with the SDSS and such. Yeah, so SDSS was a survey that occurred. It was the first digital sky survey of the sky, and occurred in the early 2000s. And Fermilab got involved in that survey at the time. This was before my time here at the lab. But I think that was the beginning of the journey of the national labs and such getting involved in doing cosmic surveys and such. So the idea, I think that the connections between the world of particle physics and the world of astrophysics, they started actually much earlier in the theoretical world, and there were brilliant theorists that worked here at the lab, and we helped shape that, the connection between the physics that happens in the early universe, the fractions of a second after the Big Bang, and the physics that can be done at the lab in terms of transitions, particle transitions, and such. And so I think that that's the connection. At the end, we are studying the same things. It's just from different perspectives.
Well, it's kind of
we are doing a large survey like this. We are focusing on the largest possible scales and studying phenomena that we cannot possibly reproduce or recreate at a laboratory. So what we can do is build big machine in many cases, using similar expertise to build the instrument. And with that, we study and we try to answer the same questions about the fundamental nature of the universe.
Now, in respect, and Jim, I'd like you to comment on this a little bit. With respect to the Dark Energy Survey, the camera that was built was actually built at Fermilab. But I would like you guys to, Jim, why don't you give us a background a little bit on, scoot in too, by the way. You're like half in the frame. Scooch in. There you go. You wanted to be cozy. There you go. Okay, Jim. So tell us about the Dark Energy Survey. What do you guys, what do you guys have? What kind of camera is it? And all of that kind of stuff.
So we built this giant camera. It's 500 million pixels. It's as big as a manhole cover. So we essentially paved the entire focal plane of the Blanco telescope with CCDs. It's fabulous. Each image is a couple gigabytes. You look through the whole image. It looks at a single CCD. We built up a collaboration.
And that means another hangout, right, Jim? Please say yes. So I'm desperate to find out what those are as well. So I have the image that you sent, by the way, over email to me with the DECam. I think it's the focal plane. Now there's all these little horizontal rectangular squares. That's the camera, isn't it? Yeah, it's the one. It's the one you sent, and it's how many pixels are we talking about here? 500 megapixel camera, folks. Is that the biggest? It never will be. Well, what's the but it's one among the largest, right? And okay, and here I'm going to go ahead and show the picture of it mounted with the 4-meter telescope that it's on. That's the composite picture you sent me earlier. I know you can't see what I'm sharing. That's why I'm describing it. So on the right side, right panel is the camera. On the left is the telescope, and with it oriented such that you can see the backplane and the camera itself up against. Okay. Okay. Hang on, guys. Okay, I think I just had a sound issue. I'm changing when I show these images. Your sound goes away. Can you guys say something? Okay. 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 Yes, I can hear them too, but it's not coming out through the. Okay, so unfortunately, it won't work if the sound is cut off when I showed those images. So we didn't hear a lot of that. But you said that it was not the largest camera ever built, and it won't be the largest camera ever built. And it's
LSST is coming. Hyper Supreme Cam on the 8-meter Hawaii is bigger. Pan-STARRS camera is probably bigger. On the other hand, as far as a functional telescope with a functional camera doing a big survey, this is world leading as we speak.
Okay. All right, folks. Well, I should have everybody back now. The problem was with the sharing of those images and the audio associated with it. So I'm back now. We should be able to hear each other. I'm sure you'll let me know if you can't. So thanks for letting me know that problem. Okay. So the Dark Energy Survey is up and running. It's been going now for how long, Jim?
Since 2012, December 12th, 2012, at the end of the main capsule, and it's beginning our survey.
Excellent date.
Oh God, I remember that date. There was all these crazy people thinking there was going to be the end of the world and
Some terrible thing.
Yeah, I remember that date. That was so funny. Oh no, it was the Mayan calendar, wasn't it? It was coming to an end or something like that. That's what it was. Okay, so the dark energy survey is looking at a wide area of the sky in the southern hemisphere, and that's limited, right, Jim, by where the camera is. It's down in Chile, and it's pretty much looking at roughly the same area of the sky the Sloan Digital Sky Survey, right?
But south, so south of the equator. So what the Sloan did was map the entire northern galactic cap. You see the Milky Way. What's not the Milky Way is galactic cap. Sloan did the north. We wanted to do the south, so we went to, and the telescope's available to us. So we went and mapped the southern hemisphere. We couldn't do it all. We don't want to do galactic plane, and we didn't have enough time to do the entire galactic cap. So we chose one of them and chose to go very deep in order to get weak lensing on a deep scale and clusters of galaxies up in near redshift 1.
Okay, and like I mentioned at the top of the hangout, whenever you're looking at this kind of area of the sky with as many nights, and these surveys are becoming much more important, and Jim mentioned LSST, which is a Large Synoptic Sky Survey telescope. It's going to be looking at the entire sky every few days over a period of many, many years, and so this time data is starting to become quite important. And so with this trove of data that they've been collecting since 2012, they've not just been looking at dark energy data, dark energy stuff. They've been looking at other things. Now, you guys will remember that back in February of 2016, the LIGO consortium announced an event. They had measured for the first time a gravitational wave event. And we did a hangout on it. The link to that hangout is in the description box. We had members of the LIGO collaboration on to tell us about it. And as they announced it, it was said that it was caused by the merging of two stellar-sized black holes. And by stellar size, we're meaning several dozen times the size of the sun, but roughly solar or star-sized black holes. Now, this did two things. It not only confirmed that gravitational waves and Einstein's theory of relativity was right, but it also said that gravitational waves can happen within the age of the universe, because nobody actually knew when or how often or how frequent they would occur, but also that these stellar-sized black holes existed. Because there's been a gap between the kinds of black holes that people thought existed, and this confirmed that there could be some in this 30 to 40 solar mass range. Well, that event happened. The Dark Energy Survey heard about this event just like everybody else did, and I'm going to let Marcelli take it from there. You guys did some stuff based on this.
Yeah, so for us, actually, the story started a little bit earlier. And the event was announced in February of this year, right? It was observed in September of 2015. But for us, the story started in 2013, when the LIGO collaboration was preparing to start observing. And they sent a message via a AAS bulletin, board, email. So I wake up in the morning and I see this email in my inbox saying, oh, the LIGO collaboration is preparing to observe, and anticipating that it will be sensitive enough to make a discovery. It invites members of the astronomical community to partner up to do follow-up observations in search for electromagnetic counterparts. So it was early in the morning. I had not yet fully had my coffee, but it stayed with me for the entire day, because I was thinking, they would not make this call if they were not fairly confident that they are going to be sensitive enough to see something. And if they do, it will be spectacular. And our camera is so well matched to the challenge of making this discovery. So after that, first thing I did was actually forward that message to Jim and say, what do you think of this idea? I got a laugh back, so the idea did not pass the laugh test. So, but then, yeah, I remember this. You did not think it was a good idea at the time. Yeah,
what? You didn't want to follow up, Jim? You didn't want to follow up on that observation?
No, this is back way before. This is when
it was 2013, right?
So the LIGO was asking for electromagnetic counterpart observers, and Marcelli said we should do this. We should arrange DES and DECam to take the data.
So part of the story was that everybody that I talked about it at the time were like, look, we're already so busy with so many different things in DS. Why do you want to do this new thing? But the thinking was, well, if they see something and we are sitting here and we did not even go and look and search, it would be a pity. It would be it would be a shame. So we should do this. We should go and observe and develop a program to attempt to do this. And part of the argument was also that in DES, we are normally making detections of supernova every night. So these would be similar to supernova, just fainter and cooler, more interesting, more exciting. So that's how we started working on this and got into a network of people that received the alert about that event as soon as it happened. So it was, I remember it was in September 2015. Wake up in the morning again and get an exciting email about an event has happened, right? And we're like, oh my, now we actually have to do something. And in that case, let's see if I remember the whole story. So the email said, the alert information that we received said it was an event of high confidence level. So it was probably something real, not a glitch in the machine or anything. And here is a map in the sky where it is most likely to be located. And I don't know if you have that map.
Yeah, you want to put that animated GIF up, Carl, for us, and I will share your screen once you've got it up. Okay. But yeah, so you were getting they were asking everybody to go look at this thing to see if you could if they could see anything in the optical wavelengths. Is that right, Marcelli?
Yeah, exactly. So and actually there was a huge response. That's when I think I realized that actually it was kind of a good idea because there were 60 other people that signed up.
Yeah.
And so there was a huge response. And amongst them, I think that our group was is particularly strong, not only because we have an awesome large camera on a system, but also because in the southern hemisphere in particular, I think our capability is quite unique. So what we did was map out as much as we could in the time available, map out the region of the sky that was most likely that the event had come from that region. And that defined the footprint in the sky where the search was supposed to happen, the search for an electromagnetic counterpart.
Carl, can you put that up for us?
Oh, I'm sorry.
You were busy. Yeah, I thought you didn't hear me.
Yeah, that's the map that's labeled 2015, September 18.
Thank you. Okay, got it. All right, here we go.
The other one that is not again.
The what?
There's a map. There is a static map. Yeah, that one. Yeah.
Okay, good. Very good.
So
okay.
That is the one that corresponds to the actual event that we observed. So what you're seeing there, the white contours are the location in the sky that was most likely, and the red hexes and orange hexes are the pointings that we did with our camera. And with that, you can see what is the typical size of a pointing on the sky, actually, which is quite cool.
Okay, so that's a pretty big area you had to look at.
Oh, absolutely. So LIGO, in some sense, it's let's say the LIGO detection is similar. You could imagine that it's analogous to detecting sound. So how do you know that the sound came from the right or from the left? You your brain manages to triangulate the position depending on how loud it is on your left or right ear and so on. LIGO does the same with these two detectors, but the precision is small, right? The precision is not great, and so that's why the region in the sky is so large. So
I think it's like the sound when your fire alarm chirps. Like you can't tell which one is it, where is it, you know, and then it goes off, and you're like, oh, I have to find it.
Yeah, exactly. Well, you have to actually just like go there and look, right? So
yeah, right, exactly.
Go there and look is what we do.
Exactly.
Well, what'd you guys see?
So we saw lots of things, lots of transients in the sky. So
Lots of things changing brightness.
Exactly.
Okay.
And in particular, our prior for the search was that whatever the optical counterpart of these events, we expected to be something that would rise quickly in brightness and then decay on a time scale of about 10 days to 2 weeks at the most. So we looked for transients that would fit that description. And at the end, we also, so we looked for transients that would fit that description. And at the end, we found none that could be a credible counterpart for the source.
So you found transients, and you found them in the rough area where LIGO says they ought to be, but they just...
But all of them were, I would say, your garden variety transients. Things like supernova.
Garden variety transients, I love it.
You know, that are interesting per se. My colleagues who study supernova would be mad at me if I said that they're not interesting. But they were just not what we were looking for.
Yeah, stuff exploding, stuff pulsating, stuff moving around, but just
garden variety transients. So none of them we could say was interesting enough that we could say was a candidate counterpart to that. So the search continues.
Well, good. Well, let me ask you this, because this goes to a question that Adam Synergy is asking on the chat right now, which I share, and I want to hear your thoughts on it. Are you confident? So this time you looked. You didn't see an optical counterpart, which led credence to the idea that what LIGO was saying about these being a black hole merger was probably no.
No. So at the time of the search, we didn't know that the event was a merger of two black holes.
But they were asking for optical counterparts to a gravitational wave event. That's all you knew.
Exactly.
Okay. All right.
Not specified what it was.
So they were being sneaky
there
then.
There are models for emission from different type of events, and we were looking for, in this case, we were looking in particular for something that would fit the description of a merger that would involve a neutron star in it.
Okay.
That's the one that actually would be most... So at the time, we actually thought that was the one that would be most likely that LIGO would see, and also the one that would have brightest emission in the wavelengths that we are sensitive to.
Got it.
So that sounded like a reasonable place to start searching.
Okay, so I like the way they did that, though. They kind of did that without telling you what they were looking for, didn't they? They were just like...
Yeah, well...
It's like, hey, guys, you see anything in your optical telescopes? What wavelength, by the way, I don't think we talked about this, Jim. What wavelength is DECam most sensitive to?
About 800 nanometers.
So infrared.
Yeah, well, so redder than
your
eyes, but you can
infrared.
see through the filter.
Okay. So
it has starting from about 400 nanometer all the way to 1 micron, and have several bands, so we can actually measure the color of the object.
Right.
So it has several filters. Some are greenish, some are reddish, some are a little bit that our eye cannot see.
And it's actually extremely well matched to the expected counterpart for neutron star merger, which is what we thought.
Okay, well, not this time, but Adam Synergy is asking, and I wanted to know too, are you confident that optical counterparts to gravitational wave events will be detected in the near future? Do you think you guys can maybe neutron stars? You said were a candidate. Another. What kind of gravitational wave events would you think that DECam might see?
So I personally think it is a matter of time, and we will see counterparts at some point. And the idea there is that it would be very unusual for such a cataclysmic event to happen without having any trace of electromagnetic emission. Now, it could be that we are unlucky and that emission is out of band for us. It could be. It's too red or something.
Mm-hmm.
But
then maybe ALMA could see it.
Then
maybe something like ALMA could see it or something.
Exactly. But then we would be able to detect it in some other wavelength.
Okay.
Now, it could be really, really faint. And if that's the case, then it means that it's not going to be easy to detect. And then it would take a long time and so on. But then it's just a matter of, integrating long enough, right? So it would be, I think, surprising if these events have, we are talking here about a very dramatic mergers of large systems. I would be surprised if they're just completely dark. But that's an opinion.
Well, let me break in. There's two classes that Marcelli's. He's actually now talking about neutron stars being broken up.
Yeah.
And we really expect to see something from them. The black hole mergers, not so much. I mean, we don't quite know if they have any optical emission, but not likely.
Yeah, that's true.
Black holes are pretty black.
Well, they could have matter around them
Sure.
somewhere.
Sure.
Not outlawed by
What
law.
about a neutron star being broken up? Like,
Decompressing a neutron star is a remarkably obvious event by all predictions of theory. It's hard to do. Basically, only a neutron star or a black hole can do it. But once it happens, you release enormous amounts of energy.
Okay. Well, I got to move along because I want to make sure we get to a lot of questions here. Here's one for you, Phil. For you, Jim. Philip W. is asking: the survey is described as probing, quote, the dynamics of the expansion of the universe and the growth of large-scale structure. What is a large-scale structure in this case?
A reflection of particle physics. Large-scale structure, if you look at the distribution of galaxies on the sky, they form filaments and voids.
A cosmic web kind of thing.
The cosmic web, exactly.
Yeah, there's this sort of weird structure that looks like a big spider web when you look at all the galaxies at very large scales.
You think that's a reflection of the initial conditions in the universe. Quantum effects that were inflated during inflation were amplified and made as big as the universe.
Right, these little tiny variations in the CMB might have set the stage for where these large-scale structures ended up.
So I have a couple cosmology questions too. One from Facebook from Andrew Planet.
Hey, Andrew!
Yeah, he's over on the Book of Faces. If we thought around the early 20th century that the universe was restricted to the extent of the Milky Way, could the universe as we know right now be much smaller than what it actually is? Hence, dark energy is a gravitational effect. I think that's what the question is. Is gravitational energy, or is dark energy gravitational in its nature, or is it something else? And kind of where is the science on that right now? Like, where's the evidence on?
Well, you're asking about 4 questions at once.
Yeah, exactly.
I've only seen one question mark, but I'm not a physicist, so I don't know how many questions that really is.
The first of all is we only see the observable universe, so light has to get here, and we can't talk about what is beyond where light can't get to us. Now, Ting, your turn.
I'm not sure what the other questions. So can you repeat the question?
Oh, yeah.
I think the essence of the question is like, kind of, what is dark energy? Is it something other than a possible gravitational effect, or is it a gravitational effect and we don't have enough evidence to really determine which one of those two things it is? I think is kind of what he's getting at more or less with this question.
I think that's exactly what we are starting. Is we want to know if the dark energy is something like caused by the space. So basically, you expand more, you get more space, and then you have more energy. Or it was some modification of the general relativity, and so that to kind of make the expansion or accelerating of the expansion of the universe. And that's kind of one of the goals of dark energy survey trying to answer. And we don't really know that answer now, and that's kind of all the astronomers and cosmologists try to get to.
Right. And
so, Andrew, if you're listening, we're working on it.
Right. Okay.
And,
okay. Really quickly, Carl, because I got to move on. I got a lot of stuff. What's next?
And from Twitch, we have random zombie generator. Is space stretching
Awesome.
over band, or is it more space being created between the space that already exists? So what is the nature of the expansion of space-time?
Astronomers will argue about that answer, and it's correct to leading order to say it's a Doppler shift.
It's a Doppler shift.
Redshift is a Doppler. To leading order, it's a Doppler shift.
Okay, well, I want to get real quick to what Ting's paper is, and then we're going to get going. But before, Coco's Hunt is saying real quick, what have they detected here exactly? And I'm going to summarize very briefly what I think happened, and it's not a detection, but these were observations that were done by the Dark Energy Survey camera to follow up the gravitational wave event, the very first one ever detected by LIGO back in 2015, but was announced in 2016 about the two black hole mergers. And what the DECam was trying to do, what the Dark Energy Survey was trying to do, was to provide evidence of anything that might be an optical counterpart to that event. And they did not see it, but they thought but they are sensitive to certain kinds of gravitational wave events, most notably neutron star mergers and core collapse supernovae, right? Marceli, am I not screwing that up? Great. So that was one paper. Now the other paper, and I know that we're covering a lot here, folks. We usually do just one paper, but we're also going to talk about Dr. Ting Lees' paper, who I'm going to let her describe what she did, and also using the Dark Energy Survey camera data to look at dwarf galaxies. Am I right?
Sure.
Among other things.
Okay, so I'll talk about a little bit. So first of all, I think we need to go backwards a little bit before my paper. So the paper I'm going to talk in detail will be one of the dwarf galaxies. We had a spectroscope follow-up on it to understand the nature of the dwarf galaxy. But first of all, when the data from Dark Energy Survey is available to the collaborator in the collaboration, we start to look for these, overdensity of resolved stars in the sky. So those are considered as a group of stars that we call them dwarf galaxy candidates. So these dwarf galaxies are the satellite galaxies of the Milky Way. So if you have a chance to go to the southern hemisphere, you can see, for example, the LNC and SMC. Yeah, the first slide, go to that one. So you can see the two kind of blobs there. They are the large magenta cloud and small magenta cloud. Those are the visible, you can see with your naked eye. Those are the two largest dwarf galaxy, the satellite galaxy of our Milky Way. They are the companion of the Milky Way. And those are just a group of stars there. And if you go to the next one, that is the sculptor dwarf galaxy, and that's we call the classical dwarfs that we know for have several decades and hundreds of years. And that's also, it's easy to see that you actually can see a kind of overdensity in the middle of that picture. However, that's kind of all the dwarf galaxy we know. I would say 20 years ago is like those. But
how many of those?
And at that time we know about a dozen of them. However, the prediction based on the cosmology model that if the universe was made of dark energy, dark matter, and visible matter, we should expect hundreds, thousands of them. And that time, it's kind of called missing satellite problem. So the satellite we are seeing that in the sky of our Milky Way are way fewer than what expected the theory says. If dark matter, we understand our universe with the standard model with dark energy, dark matter. So that's kind of the missing satellite problem. It's a kind of a challenge for if the dark matter is a cold dark matter. And they have to use other alternative dark matter model to explain that why we don't see that many as what we predicted. And when Sloan turns on, the Sloan Digital Sky Survey Marceli mentioned, then there's another about more than a dozen of ultra-faint dwarf galaxies were found. So it's a new class of dwarf galaxies. It's not like the sculpture that you can see very obviously. That here we are showing one of the ultra faint dwarf galaxy that's discovered using the dark energy camera. It's called Rectangular II. This is the image taken by DECam. If you look at it, you don't see a kind of a group of stars obviously in the center of this picture, and it's hard to say it is a dwarf galaxy there. And so we need a kind of more sophisticated analysis to confirm that it is actually a dwarf galaxy candidate. And what we did is some analysis, and then if you go to the next picture.
Wait, hold on. Don't leave this yet. I'm zooming in here.
There's nothing there.
There's nothing there. Okay, good. Okay, I didn't see anything. All right. Okay, go ahead then.
We go to the next slide. I don't see the slides anymore.
There we are. Reticulum 2.
Yeah, then go to the next slide. Here, what you see is the same picture as the last one, but we remove all the bright foreground stars, and the left are those statistically we think are likely to be the member of those stars. And you can try to link the two and just give people a feeling that what are the members of that dwarf galaxy and which are not the member stars of that dwarf galaxy.
Okay, hang on before you start blinking there, Carl. Okay, I got to get the thing back. Okay, go ahead and blink. Just go back and forth. Go back and forth.
Back and forth, quickly.
There you go. There you go. There you go. Whoa, too far. Too far. There. Oh, way too far. Way too far. There you go. Back and forth. Back and forth. There, right there. You got it. Hey, all right. High tech.
That is my video game skills for you.
All right.
Yes, correct.
Yeah, so you can see that compared to those classical dwarfs, it's really hard to discover them, first of all, because they are really faint stars, and there are very few stars compared to, like, say, Large Magellan Cloud and the sculptured classical dwarf galaxy. Okay. Stop linking us enough again. So
you're gonna give Ting a seizure. Okay.
But I want to say, so what we do is we find these kind of associations, and then we feed them, and we go back, to keep them. So we kind of select these stars as the candidate members for a dwarf galaxy, and then we feed them to a spectrograph, and then we measure line of sight velocity of those stars to confirm which star belong to the member and which star belong to the dwarf galaxy and which star are not belong to the dwarf galaxy. And the most importantly, when we discover them with a dark energy camera, we think they are a dwarf galaxy candidate, but we want to confirm that they are dwarf galaxies. That need to know. For us, we need to know what is a dark matter mass, or say what is the total mass, because we know these, if they are dwarf galaxies, they must be dominated by dark matter, not visible matter. So we need to go follow them up and get their line of sight velocity. And from the line of sight velocity of individual star, we can calculate their mass of that system. And so now I'm going to talk about detail of the paper that we work on. Was next slide. It's called Eridanus II. So that one in the center, you can kind of see that is the brightest dwarf galaxy we discovered using dark energy camera. And you can see kind of the bluish stars there are the Eridanus II dwarf galaxy candidate. But when we discovered it with dark energy camera, it is just a candidate dwarf galaxy. And then we followed it up with another instrument, another telescope, not far away from the CTLO, the Blanco telescope. It's about 4-hour drive. It's also in Chile. And we followed up with that spectrograph on the telescope there. And then we get the mass of this dwarf galaxy. And then we calculate something called the mass to light ratio. So the mass is the total mass. The light is the light emitted by the visible light, which is the light emitted by the visible matter, which is from the star. So we get to the dark matter, or say the total mass, versus the stellar mass, and we got about 500 solar mass to solar luminosity. So this mass of the sun versus the mass of the mass of the sun versus the light of the sun illuminating. So the sun, right, the mass to light ratio is 1, and you can imagine for this dwarf galaxy candidate, the mass to light ratio is 500-ish. That is telling us that in one star we are seeing there equal to 1 solar luminosity, we are seeing 500. We have 500 dark matter there that we are not seeing visible. So
Okay.
that is telling us that this dwarf galaxy is real, the candidate is a real dwarf galaxy that's dominated by dark matter. And that's kind of one follow-up on one of the dwarf galaxy we found.
Okay.
And we found around a 20-ish dwarf galaxy from the dark energy camera and also other surveys. And we need to follow all of them and to understand their property.
Okay, you've given us a lot to digest, so I need to go back a little bit. Okay, I want to make sure that because I want to. There's a lot of stuff that you just explained to us. So the dark energy survey, by looking out at the area of sky that it does, has so far been able to determine or discover these areas of what you're calling overdensities. These are just things that seem to have more stars in them than the surrounding area, but you don't know for sure what it is yet. So you look closer, you think they could be dwarf galaxies. But in order for them to be dwarf galaxies, they have to have a lot of dark matter in them. That's what you said. And so for this dark matter to be, and it has, so you then you measure the light using other telescopes besides the DECam to measure the light from these galaxies, these overdensities, to try and get a sense, and then you measure their velocities, their motions,
From Doppler shifts.
From Doppler shifts, and from those two things, you were able to get this thing you called a mass to luminosity ratio.
Yes.
Which is, in the sun, a mass to luminosity ratio is 1. There's one solar mass, it lets out one sun's worth of luminosity. But you're saying, if it's a dwarf galaxy, if your overdensities that you're seeing in DECam are in fact dwarf galaxies, then they need to have this mass density ratio or mass luminosity ratio of 500 to 1. For every, what is it again? For every one star, it's 500 times more massive?
Yeah, but
right?
For this one, it's about 500. But in general, so usually we call, if the mass to light ratio is under, say, 10 or under 5, then it's not dark matter dominated. Then we call it a star cluster or a globular cluster. But for a galaxy to be a galaxy, it has to be dark matter dominated at that kind of luminosity. And for the Eridanus II that we are starting, based on the measurement we got, the mass to light ratio is 500. But for the ultra faint, in general, the mass to light ratio is between about, say, 100 to, say, 1,000.
Wow, okay. Well, Carol, I want to hear your thoughts on this. You're a globular cluster person. You must worry about this idea of when am I not looking at a globular cluster anymore, and when am I looking at a dwarf galaxy? Is this something that you care about too?
Actually, it's worse than that. I actually observed a long time ago a dwarf galaxy called LGS3, which was discovered a long time ago. And shortly afterwards, I was convinced by Brent Tully to observe it. And I told him that I didn't think it was anything, and it would be good to do flat fields with the CCD because it was absolutely featureless. Turns out we did observe it, and it is one of these little dwarfs. As far as I know, it has a lot of hydrogen in it, but I'm not sure about the mass to light ratio because I'm sure it's been studied since then, and there are different statistics, but I don't think it's 100 to 1. But globular clusters are rather different because they have very healthy populations, and there is not much evidence for them. Another question is the age of the dwarf galaxies. The globular clusters are very, very old, and in general, because of their orbits, which are in general ellipses, they've passed through the gas of the dust of the disk in their parent galaxy many times, except for ones that are in ellipticals. So they tend not to drag along a lot of dark matter with them. And also the particular motions of globular clusters have been well studied. So that motion has been studied as well as it can. And I don't believe there's much evidence for something like 100-to-1 mass to light ratios in those objects. Okay,
well, this is an interesting idea for me because I hadn't heard that. Yeah, there must be a point at which when you're looking at globular clusters, these overdensities stop becoming just a bunch of stars and they become these dwarf galaxies. It's kind of like that. It seems like a gray area, kind of like when people think, well, when does a brown dwarf become a star? That kind of thing.
They are, but globular clusters are demonstratively old, and there's no evidence of star formation. Some of these dwarf galaxies, the question is, why did they, like, you have the LMC and the SMC, they have a lot of star formation. So our guests can speak to why did these other objects, why did they stop, if they have a lot of mass associated with them, why did they stop star formation?
Well, yeah, that's something people trying to study as well, and that's actively kind of study field, I would say. And so all these ultra-faint dwarf galaxies that the satellite of Milky Way turns out to be also ancient and stopped forming stars, say, 12 giga-years ago. So they are not forming stars. And also the Eridanus II paper actually is particularly interesting because it is one of the farthest satellite galaxy of Milky Way. And from the photometry, originally people thought that there may be some star formation, a recent star formation showing from the photometry. And the follow-up paper, that the spectroscope follow paper that we wrote, basically said it seems those are not true, that this one also does not have recent star formation. And then it's a question, say, why all these ultra-faint dwarf galaxies shut down or say stop forming stars a long time ago, while LMC, SMC, like those massive satellites of our Milky Way are still forming stars. There's a lot of way to explain that. Some people think, for example, LMC and SMC may enter the Milky Way recently, maybe 2 giga-years ago, while those ultra-faint were started and become the satellite of Milky Way a long time ago. And the gas that in those satellite galaxies, because they have been orbiting Milky Way for a long time, the gas has been stripping away. So there's no gas, there's no such reservoir to support them to forming stars. Okay, and another possibility is that those ultra faint, they are much, I would say they are fainter, much fainter than like LMC and SMC, but they are also less massive than LMC and SMC.
Yeah.
So somehow, as the total mass of the dark matter subhalo decrease, somehow the capability of star formation in the subhalo also goes down dramatically. And there's different mechanism to explain why that is related to the mass of these dark matter subhalo, or say these dwarf galaxies. And the people are trying to understand them. That's including something called tidal stripping or like reionization.
What's the supernova blowing out the gas?
There's no
idea. In the early days of the stars, when they were first forming back 12 billion years ago, there was a huge set of supernova going on, and it just blew off the gas.
Sure. But so that's why people are trying to understand maybe the reionization at the very early of the universe, like 12 or 13 giga-years ago, somehow also turned down all these star formation, or it may be related to the interaction between the Milky Way host and all these dwarf galaxies that prevent the dwarf galaxy forming more stars. But it's something that people trying to study the dwarf galaxies and also trying to observationally and trying to run simulations and then try to understand that. So I would say dwarf galaxy is really important in two ways. One is to understand this galaxy formation in the smallest scale. Another to understand the nature of dark matter. That's why it's kind of exciting that we have like about 20 dwarf galaxy candidates discovered in the past 2 years. So people have more targets to follow up and to understand them.
Okay, are dwarf galaxies relatively not, I mean, are there just not that many of them? And you said that in the DECam has found roughly 20 in our neighborhood. That doesn't sound like very many. Are dwarf galaxies ubiquitous? Are they pretty rare?
So as I said, that I would say 20 years ago, before Sloan turned on, there's only a dozen of dwarf galaxies we know while the simulations show there should be hundreds to thousands of dwarf galaxies. And that time, people really think that maybe our cosmology model was wrong. But now, as we are finding more and more, we just noticed that because we didn't have that depth to go faint enough to see all these dwarfs in the past.
Colors.
Okay.
And so I want to say is LSST, if the cosmology is correct, and we found 20 of them now with DECam, we with LSST, the next big telescope turned on, we should be able to see hundreds of them.
The photographic space is plenty deep enough.
Okay. Running out of time, I got to get some questions. Adam Synergy is asking, how far away is Eridanus II? Is it falling into the Milky Way's gravitational potential?
So physical units is 300 kiloparsec.
Light years. We're calibrated for light years. How many is that?
Times 3.
Times 3.
Okay.
Times 3.
No, you have some zeros there too.
Well, pi. Okay, it's pi times parsec.
So it's one of the first. It's almost at the edge of the Milky Way dark matter halo, I would say. And I would say, just give you an idea, at 500 kiloparsec, we probably don't really call it belong to Milky Way anymore. So it's kind of at the edge.
So it's right at the edge, and that was my question. So these are all satellite galaxies of the Milky Way, and I was just about to ask you. You said how far away was it again? Beyond which they're probably not.
So some of them were discovered at 20 to 30 kiloparsec. That's the closest one.
Right.
And the Eridanus II is at 300, so 10 times further than the closest one that we found.
Okay.
So all the dwarf is between 30 to 300 kiloparsec, and I would say 300 kiloparsec is kind of around the edge of the Milky Way halo.
Okay, one more question, and then I think we're running out of time. Care Bear is asking, on expansion at the smallest scales, are the new little pieces of space popping into existence somehow, or is the volume of the existing space getting larger? Or is it something else? What are the educated guesses?
Okay. All right. So you can think of. Okay. So I think I understand the question. So what is happening is that when the universe is stretching out, the scale is stretching out. Right, so it's if you would be holding a scale and you have something that is 10 centimeters long, and you close your eyes, you open again, and now the universe has expanded by a factor of 2. You would have that amount, that empty space that you had originally that was 10 centimeters. It's now, compared to what it was before, it's 20. But it's not that you would take a new ruler, put it there, and you would measure 20. You would measure 10 because your ruler also expanded together with the universe.
But so that's an interesting explanation. But I would like to just offer what I always imagine, and you can tell me if I'm really far off. It seems to me that the stuff that is space-time, as it gets larger, as it expands, and you say the scale increases, that's true, but that's because you're actually getting new space-time being created out of this, right?
Well, if you're counting new space-time with respect to what you had before, right, in terms of, okay, if your reference point is the initial point, then the next point you would say, okay, now I have more units of empty space in my universe. You could think of it that way. But if you are in this universe in the future where the universe has already expanded, you will not count more units of empty space in between things because everything else, including the scale that you use to measure, it's also expanding.
So just chew on that, Care Bear. Okay.
It's very subtle. It's very hard.
It is. It is so hard to accurately describe in a way that you can visualize.
But there's not spontaneously stuff being created.
I don't think so.
Popping up. At least there's no evidence so far that there's new stuff.
That's not true. There's this vacuum space idea of vacuum space,
else, but not matter, as we know it.
Well, there's this vacuum space energy that's supposed to be able to be created from nothing. So that's what a lot of people. It could be that.
The questions that people use, the way people actually tend to pose the problem is if you put a rope between two galaxies, what happens? And the answers are not so obvious.
The rope gets bigger, is what Marcella would say. Right? Yeah. Okay. All right. Yes. So there you go. On that, we're going to have to let you chew on that for a while. But I am just really thrilled to have these guys with me. This has been a long-standing desire of mine to have members of the Dark Energy Survey on our Hangouts. So thank you guys so much. I really hope you'll agree to come back and talk to us some more about the various things you guys are doing. I'm putting you on.
We're looking forward to it.
Thank you. Okay, and I really want to learn more about the cosmological papers when they come out and find out the answer of what is dark energy, because you guys are going to answer that for us. So I appreciate that.
Yeah.
Working on it.
Yeah. In fact, the title of your paper should be "Dark Energy is ... and then we'll just read the paper to find out what it actually is. So thank you for that. I appreciate your effort. And with that, all right, Carol, well, we got another one ahead of us. Thank you for setting this up. This has been a lot of fun. Thank you all for joining us. Also, thank you to Carl.
Thanks for the invitation. It's been fun.
Yeah, you guys were awesome. Great.
Glad
Thank
we
you.
got you guys.
Yes, and
great idea.
As you get more observations, Ting, I want to hear more about these candidates that you've got going. I want to hear about whether they are there or not. And when you get some visual confirmation of some of these gravitational wave events, Marceli, I want to hear about those as well. So thank you very much for joining us. Okay, well, that is it for this Astro Coffee Hangout, everybody. I want to thank you all for watching. Next week is our Future in Space Hangout, where we will have members of the LUVOIR team. That is the large UV optical infrared, basically everything telescope that you're ever going to want to see in every wavelength. Team that is going to be launched after the WFIRST telescope gets put up into space. They're going to tell us what they can see and why. So that'll be next Thursday. I also want to let you guys know that if you want to learn about these Hangouts, go to deepastronomy.space/Hangouts. I've got a calendar there where once we get them finalized, I put the links and everything into the calendar. So that's how you can learn what's coming up next. So please check that out. On behalf of Carol Christian, Carl Clark, and our guests, I want to thank you all very much for watching. And as always, keep looking up.
Looking out.